Hi, it's Paul with a script that's completely different from the mathematical one for this week. This is designed to be an inspiration for you to create a clever data set of your own. My grandson Will and I are fond of playing the online game Path of Exile, and once you get your character up to a high level, you can run through various maps, slaughtering monsters, and you are rewarded with experience points, XP, and loot. So I kept track of what happened for a fairly large number of these maps and summarized the results in the file xploot.csv. So each entry in this data set has the name of the map, the level of the character that was running it. Levels in this game run from 1 up to 100. The amount of experience gained in running the map, and a number that's my effort to assess the value of the loot that was collected. There are 4 maps that participated in this data set. Beach, Graveyard, and Lookout are Tier 1 maps. Marshes is a Tier 2 map, and Beach is everyone's favorite Tier 1 map. I think it's generally believed that Beach is more rewarding than either Graveyard or Lookout, but that's going to be for you to figure out. Character level 69, you're just starting to run maps. Character level 80, you're well into this. And the official documentation for the game says when you run a map with a character whose level is much higher than the level of the map, that over-leveled character is penalized by not getting as much experience. I'm regarding higher than 76 as being over-leveled for purposes of Tier 1 and Tier 2 maps. If you look at a histogram of the experience gain, you'll see that it's normally a modest positive value, but there are lots of outliers on both ends. And the reason for that is if you die while running one of these maps, it costs you about 10 million experience points at this level. And in the league that recently ended, every once in a while you hit an abyss, and that gave an opportunity to collect a lot more experience and loot. And as a result, the histogram of the loop again has a long tail off to the right. This looks kind of Poissonish, doesn't it? It goes up and then goes back down. And I figure the way I am counting loot, very valuable items like chaos orbs and abysses each contribute about 30 to the loot value. So maybe loot over 30 has a Poissonish distribution. No, I guess it really doesn't. One of the things that I'm going to ask you to do is to see whether the data set that you collect is appropriately modeled by any of the distribution functions that you've heard about. Sometimes it is, sometimes it isn't. In statistics textbook, there's a model for every data set, but in real life, that's not so. However, as you've been seeing, if you average something enough times, you're pretty much guaranteed to get a normal distribution. So let's suppose we took 10 runs through these maps, chosen at random. I'm sampling 10 times from XPL loot. If I plot a histogram of that, the histogram looks roughly normally distributed, and we know just the parameters for that normal distribution. The mean is the mean loot collected, and since averaging 10 samples decreases the variance by 10 and the standard deviation by the square root of 10, I take the standard deviation of the LUT, divide by the square root of 10, and bingo, we have a pretty good match to a normal distribution. This is something you can do with more or less any data set. It doesn't say much about the data set itself. It says we've got to get busy and prove that central limit theorem that explains why this happens. Now, you might expect that when you gain more experience, you've had a good run and you'll gain more LUT. An appropriate measure of that is the correlation. So I call the COR function. And I discover I've got a correlation of about 53%. That's pretty good. If I do a scatter plot, you can see that indeed high LUT and high correlation and high experience gain do seem to go together. Later in the course, you'll learn how to do linear regression. You can sort of eyeball a straight line that runs through this and sort of fits the points. But at the moment, what we've got at our disposal is a bivariate normal distribution. I can't see any reason that these quantities should be modeled by a bivariate normal distribution. In fact, I can see a number of good reasons why they shouldn't, but let's try anyway. So let's make a vector of means. We've got the mean of experience gain and the mean of LUT. That's going to be one of the arguments for our multivariate random number generator. Then we compute the standard deviation of the experience gain, SDXP, the standard deviation of the LUT, and now, as you may recall, we can put together the covariance matrix that the MVR norm function wants as its input. So, I make a 2 by 2 matrix where down the diagonal I have the variance, the square root of the standard deviation for the XP gain and the LUT, and the two off-diagonal entries are the product of those standard deviations along with the correlation. Now I've got to load the library that has the multivariate normal generator in it, and since I had 50 maps, I will generate 50 samples from a bivariate normal distribution in accordance with the means, variances, and correlation that came out of the data. I still don't understand why plot does not always accept add equals true as an argument, but I and a couple of students in the class independently have found the fix. If you call the R function points, that automatically overlays data on an existing plot. So I said overlay the samples that we generated from our bivariate normal distribution in red on the existing plot, and you look at it and say, that's a pretty good match. Looks good to me, but in fact this is phony. We matched the means, we matched the variances, we matched the correlation. Sure enough, the samples are going to match fairly well, but I don't think that the bivariate normal distribution is a particularly good model for this. It's the only one we've got. Okay. Now let's do some hypothesis testing with these data. There is a well-known formula for the decrease in experience when your character is over-leveled for the map. Of course, a higher level character is going to be better at gaining experience, and so that's an attempt to compensate for the high level of your character. And it's worth checking whether the net effect is to decrease your experience. So let's try this with a permutation test. I don't want to type in this whole thing over and over again, so I will copy this vector into a new vector xp, And now I have created a logical vector named over that has true whenever the level is higher than 76, which gets the indices for which we're over leveled. And you can see 1, 2, 3, 4 we're not over leveled, but 5 and 6 over leveled is true. And I can compute the mean experience gain for the over leveled characters, the mean for characters that are not over leveled, which looks substantially greater, but we now can do better than saying looks substantially better. So for my observed difference, I'll take the mean for the characters that were not over leveled minus the mean for the characters that were over leveled. That's a difference of almost 2 million experience points. Now we'll run a permutation test in the standard way by scrambling the over vector. So I will sample over, extracting without replacement a number of samples equal to the length of the vector. In other words, I'll just generate a random permutation of the over vector. And then I will compute IDX as the set of indices for which this scrambled vector has over leveled. And I'll compute the difference the same way I did before. Make a histogram of it, approximately normal. And on that histogram, I will put a vertical red line corresponding to my observed difference. And I look at this and say, well, there's a small probability that a randomly chosen subset of the maps would lead to a bigger difference than that. But it looks to me as though this claim that you lose experience when you're over leveled has considerable merit to it. And if I compute the p-value, I get a p-value of about 3%. Now for loot, there's no explicit advertised penalty for being over leveled. But maybe there's a decrease anyway, so let's try it out. So we'll regenerate this over-leveled logical vector, store the loot column from the data frame in a vector that's easier to type, and generate the set of indices for the over-leveled cases like that. Compute the mean loot when you're over-leveled, the mean loot when you're not over-leveled, and what do you know? The loot was actually slightly better when the character was not over-leveled. So my observation is that difference. The loot is on the average about 7 points higher when you're not over-leveled. And we run exactly the same sort of permutation tests. Scramble the over column, look at a histogram of the results, plot the observed difference, and it's smack in the middle. You say, a very substantial fraction of the time, choosing a random subset of these maps leads to a difference that's greater than what we'd observed. In this particular case, we got a little more loot when we weren't over-leveled, but that's not a significant difference. And if I look at the p-value, it's 32%. This technique will work on more or less any data set you collect. So what I'm going to ask you to do on the homework is preferably create your own brand new data set the world has never seen before. If you're feeling lazy, go to the internet and find a data set, and then do some display, some computation of things like means and variances, some attempts to model with existing distributions, and test a hypothesis or two. In section, I'm going to have a workshop problem where you attempt to confirm whether running the Tier 2 marshes map gives a statistically significant extra amount of loot and/or experience points.